Okay, this is lesson 6.4 and 5, transformations of sinusoidal functions. The transformations of sinusoidal functions follow the same general rules that we've discussed in previous chapters for any function. And that's, you can transform it four ways. You can have an A, a K, a C, or a D. K and D acting on X, so those are your horizontal transformations. K is the multiplier, so that's the stretch or compression. D is the add or subtract, so that's the shift horizontally. In terms of A and C, A is multiplying onto the function, so it's the impact on Y, stretching the Y's or compressing the Y's. Also reflecting is built in there too. C is the adding part, so it's the shift up or down. The parent functions in sinusoidal can either be the sine curve or the cos curve. And we discussed in the first lesson that they're the same curve, it's just a shift. So you can actually write sine in terms of cos or cos in terms of sine, it's just a transformation. But for our purposes, that just means we're going to use a different 5 key points. If we're talking about a sine curve, we're going to use the 5 key points for sine as our parent function. And if we're talking about cos, we're going to use the 5 key points for cos, and we're going to transform those. What do A, K, C, and D stand for? Well, to review, here are the effects on any function, but specifically the sinusoidal in this case. They're no different than the effects from other functions. So we should be able to fill in this table already based on prior knowledge. The new piece is what the A, the K, the C, and the D stand for in terms of the sine function. They have additional names or features. So that A, we kind of talked about in the first lesson, it does the reflecting or the compressing or stretching vertically, but that A also represents the amplitude of your sinusoidal function. So on the graph, the A, whatever the A value is in the equation, will tell you the distance from the axis to a max or a min. K, since it's the horizontal stretch or compression, has a direct relationship to the period. The period of sine or cos is 360 degrees. So if you've stretched or compressed horizontally, you're changing the period. And the relationship is that K is equal to 360 divided by the period. Alternatively, you could write that the period is just 360 divided by K. It's supposed to be a K. And well, how does that work? Well, let's think about it like this. If K is bigger than 1, it's a horizontal compression. If you're taking something that's this big and you're compressing it horizontally, it's getting smaller. So that means that the period should be getting smaller too. If the horizontal compression factor was, let's say, 2, we're taking that sine curve and we're compressing it into half the size, well, the period should be half as well. So that period that was 360 divided by 2 should be now 180, and that's how the compression relates to the period. So that's a nice relationship. If you know the equation and you can pick up the K value, you know what the period's going to be. If you take that K value and divide 360 by that K value, you'll get the period. D just stands for phase shift. There's not any unique feature there. But C represents the equation of the axis. So that C value in the equation is also the equation of the axis. And what you might remember, that equation of the axis is the line that runs right through the middle of the curve. It's like your equilibrium. It's halfway between the max and the min. So how do we do these transformations? Well, those key points I was talking about, for sine and cos, the angles are 0, 90, 180, 270, and 360, and the y values come from the curves. So for sine, it's 0, starting at 0, going up to 1, back to 0, down to the minimum -1, and back to 0. Cos starts at a maximum, 1, and then goes down to the minimum -1, and then back up to the maximum of 1. And if you remember those 5 key points, you can do your transformations just simply by picking out A, K, C, and D, making your mapping notation and transforming those 5 key points, just like we did with any other function. So there's not really much new there. But let's kind of review how to pick out those features from an equation and then relate them to the features of the curve. So it says describe the graph g of x. If g of x is -3 cos 720 minus 5x plus 7 describe the transformations of the parent cos x. So as you can see, we don't have the k common factored out. So I'm going to put a star here. Always common factor k first. If you don't common factor your k, you're going to get the wrong transformations, and that's for any function. So I'm going to rewrite this, negative 3 cos. I'm going to write the negative 5x first so it's easier to see what we're going to common factor. And that'd be plus 720 plus 7. And now I'm going to common factor that negative 5. If we common factor negative 5 from the first term, we end up with x, and from the second term we get negative 144. And now we have our function common factored. So off to the left here, I'm going to write my a, k, c, and d, and then we're going to write the words for the transformations. So a comes from the number in front of the function that's multiplying. So negative 3 is our a. C comes from the adding or subtracting to the function. In this case, it's 7. K is the multiplier in front of the x, so the thing we common factored out. And D would be the value adding or subtracting to x, and remember it's the opposite sign. So if we have x minus 144, D would just be 144. And from the A, K, C, and D, we should be able to describe those transformations. So we'll start with A. A is negative 3. So we have a vertical reflection, or you can say reflection over the x-axis. Since A is 3, that's a vertical stretch by factor of 3. K is negative 5, so we also have a horizontal stretch, or sorry, a horizontal reflection. And since K is 5, that means we have a horizontal compression by a factor of 5. And remember, the factor should always be a number bigger than 1. So if A or K are a number less than 1, we're going to flip that fraction to get our factor. A shift, 144 is our phase shift, and that would be to the right. So right, 144 degrees, and up, because C is positive, 7. And these are our transformations. So these are the transformations that we can describe based on the A, K, C, and D. Not sure what happened here with the tan. I'm going to cross that out. That shouldn't be part of it. Determine the period and phase shift of each of the following functions. So if you look up here at that chart, the period is related to K. So if we can get K, we can find the period. The phase shift is the D. So this question is really asking us to find K and D and then interpret them. So I'm going to do the cos one, and I'm going to leave the sine one for you. Notice our K is not common factored. So the key to this question is common factoring. Common factor the 3, we got x minus 60. 3 is K, and D is 60. So, oh, sorry, can't see that. D being 60, D is the phase shift. So we have a phase shift of 60 degrees right. And since K is 3, we can use that little mini equation that we have up here at the top. Period equals 360 divided by K, and that'll always be the equation. So the period is 360 divided by 3, which is 120 degrees. So that means that there's going to be a full sine curve, or sine wave, wave's better, a sine wave cycle in 120 degrees. So if we were graphing from 0 to 360, we would expect to have 3 full cycles. That's what the K is telling us. All right, you can try B on your own. You can pause the video now and try it, or you can wait till the end of the video, come back and do it. Make sure to check your answers on the course website. All right, let's try to graph one of these. So there's actually 4 here to graph. I'm going to demonstrate one of them, and I'm going to get you to graph all the other 3. Whether that's in class tomorrow, you'll have some time in class, or if that's after the video, that's up to you. Let's do A. We have a scale here and axes right in the middle, and both of these graphs will end up on the right side because we're going to graph, or we're going to fix where we're going to graph it. We're going to graph this between 0 and 360, or we're going to try to graph it on the right side. Based on our shifting, we can kind of anticipate where we might end up. Like if we look here, we have a shift of 90 degrees to the right. So instead of starting at 0 degrees, we're going to have a graph that's shifted over 90. So we expect a graph somewhere in this section of the graph. And that's okay. I'm not super picky on where you're graphing it. I'm just going to get you to take those 5 key points, transform them, and then wherever it ends up is where it ends up. And however many cycles there are, that's how many cycles you're going to graph. All right? So since we're graphing sine, we're going to start with the parent function for sine. And hopefully this isn't too hard for you to see because I'm going to write over the grid on this side because we're not actually going to graph here. My parent function is x and y, and the x's that we use are 0, 90, 180, 270, and 360. Now I could write theta and y instead. That might actually be better, but x and y, poor communication. I wouldn't dock you on your test, so I'm not going to change it. And your y's would be 0, then 1, then 0, then -1, and then 1. And if you ever forget, sorry, not 1, 0. And if you ever forget those 5 key points, well, the nice thing is you have a calculator. You can just type in sine 0, sine 90, sine 180, sine 270, sine 360, and get your y's. You really just have to remember the 90, 0, 90, 180, 270, 360. All right, we've got our table representing our parent function of sine. Now we need to pick out the A, the K, the C, and the D. So here's our A, because it's the multiplier in front. There's your C, it's the adding. It's already common factored, lucky us, K. And our D is 90. So what we're going to do is we're going to write some mapping notation. We'll start with the x's. The x's are x over k plus d. So if I fill that in, I get x over 1.5 plus 90. It's a little sloppy to have a decimal and a fraction, but we're going to leave it because we're just going to use that tool to come up with our points and then kind of ignore it. The y's would be ay plus c. Our a is 1.5 and our c is 2, so we get 1.5y plus 2. Time for a new table. This is going to represent our transform table. So I'm going to write my x over 1.5 plus 90 and my 1.5y plus 2. And let's do some mental math. 0 divided by 1.5 is 0, plus 90 is 90. 90 divided by 1.5 plus 90 is 150. And hopefully you trust the rest of my math because I'm not going to dictate all of these. 210, 270, 330. And for my y's, the nice thing is the zeros, there's 3 of them. So when we multiply 1.5 by 0, we're going to get 0. And then when we add 2, we're going to get 2. So we got 2, 2, and 2. Because C represents your axis, so we should be balanced around the axis, and we are. The max should come from inputting the 1. 1 times 1.5 is 1.5, plus 2 is 3.5. And that makes sense because A represents the amplitude. We're going 1.5 above the axis too. The y's you can probably figure out just by looking at the equation, but mapping notation will keep it solid for you. The minimum should be 1.5 under 2, which is 0.5. And you can get that by inputting the -1, and you end up with 0.5. The hardest part of coming up with this graph is the x scale and building your scale. Reasonably, though, using just the features of A, K, C, and D, the fact that the period is impacted by K, and that's the amplitude, and that's the axis, and that's the phase shift, you can graph it without even building a table and using mapping notation. And if you can practice that skill, that's a totally acceptable way for you to graph the sine or cos curve. It's just that mapping notation keeps it solid for you, and it's something you can always rely on to give you the graph, and it'll always work. Scale for our graphs. I'm going to use 30 degrees for every one of these little boxes, just so both of these graphs are going to fit on there when we do the second one. So 30, 60, 90, another 30, 60, and 180, 30, 60, and 270, 30, 60, and 360. And that's actually a big enough scale for us to fit on our first graph. The maximum is 4 or 3.5, so we're going to go up to about 4. For the other graph, we have to actually go down a little bit more, so I'm just going to do 0.5s for my scale. So 1, 2, 3, 4. 3, 2, 1. There's my 0, so that would be -1, -2. And that should be enough for you to get both graphs on there if you try to do B. And then we just plot our points. 90 and 2 is a point. 150 and 3.5, so that would be 120, 150, 3.5. 210 and 2. 270 and 1.5. Or sorry, 0.5. And 330 and 2 again. And there we have our points. And then keep in mind the shape. It's not straight lines connecting these dots, it's a curve. So we go up, down, and back up. And this graph continues, so we're going to put arrows extending past the points. And there is our graph of A. I'm not going to write the equation. All right, and that's graphing using mapping notation. Try B, C, and D. You get to be a little bit more creative coming up with your scale for C and D, but if you use the same scale I used on this graph, C and D ones work out really well too. You just have to go into the negatives a little bit, but that's okay. Take a shot at those 3 graphs, and yeah, that's it for lesson 6.4/6.5. Thanks for watching, and I'll see you next time.